Ankita.
Present, sir.
Okay. Chandrasekhar Pattar. Chandrasekhar. Harshgowda. Harshgowda. Janvi.
Present, sir.
Right. Mahadev. Mahadev. Mohammed.
Present, sir.
Right. Kirti. Kirti. Pikesh. Pikesh. Prajwal Gowda.
Present, sir.
Right. Ramesh. Ramesh. Ratan.
Yes, sir.
Okay. Rohan. Rohan. Rutik. Rutik. Rutvik.
Present, sir.
Right. Sadashiv. Sadashiv. Sagar. Sagar. Sai Prakash.
Present, sir.
Okay. Samir Ahmed.
Present, sir.
Right. Sania.
Present, sir.
Okay. Sanjay. Sanjay. Sankalp. Sankalp. Sanket.
Yes, sir.
Right. Shiraj.
Present, sir.
Okay. Shivnanda Natikar. Shivnanda Natikar. Shraddha. Shraddha. Shubham. Shubham. Sumit. Sumit. Suraya Banu.
Present, sir.
Right. Tejas. Tejas. Vivek. Vivek. Yamunappa. Yamunappa. गावकर रजत रामचंद्र. गावकर रजत रामचंद्र. मंजुनाथ. मंजुनाथ. प्रथमेश. प्रथमेश.
Present, sir.
Right.
Present.
Joslino. Okay. Joslino. Joslino. Tejas has joined. Anybody else? Anybody else joined? All right. Are you able to see the screen here? Screen is visible?
Yes, sir. Yes,
Right.
sir.
Okay, thank you. In the previous class, we were discussing about the emitter follower configuration. We have discussed that the output at emitter follows the input at the base terminal, hence it is emitter follower configuration. It is also called as common collector configuration. Then we have discussed about the RE model, its equivalent circuit, and the RE model of emitter follower configuration. Then later we have derived the performance parameters of the emitter follower configuration considering the RE model of this emitter follower configuration. You will have to remember the formulas for the various performance parameters of emitter follower configuration, because they will be used in further circuits, other circuits. Here we are finding the value of Zi, right? To find the value of Zi, we are applying the input voltage. We are writing the equation for input voltage Vi, and then we are getting the equation for the Zb first. Zb is given by beta small re plus 1 plus beta into capital Re. Remember this equation. Zb is beta into small re plus 1 plus beta into capital Re. Then Zi is Rb parallel Zb. Input impedance Zi is Rb parallel Zb. Remember this equation. Then here we are finding the Zb is further simplified as beta into capital Re only. Output impedance Z0 we are obtaining from the KVL equation. We are first simplifying all these equations, and then we are getting it in the form of a KVL equation. The KVL equation is Vi is equal to I into small re plus capital Re. This is the KVL equation. If we draw this KVL equation in the form of a circuit, then we get this is Vi. This is the current I into small re plus I into capital Re. Here there is a node. Therefore, we are finding the value of the output impedance and the output voltage or the voltage gain from this particular circuit. To find the output impedance, we are shorting the active source, that is making Vi equal to 0. Therefore, the output impedance is Re parallel capital Re. Small re parallel capital Re is the output impedance. Remember this main equation. Then this is simplified as Re plus capital Re is capital Re only. Therefore, Re and Re will get cancelled here, right? Re plus capital Re is capital Re. Capital Re cancels, and only Z0 is equal to small re. Further, voltage gain equation. We are applying the voltage division rule to this circuit. Therefore, we are getting the voltage gain equation. The output voltage equation is given by the main voltage Vi into resistance of the same branch divided by sum of the resistances. Accordingly, we get V0 is equal to Vi into Re divided by small re plus capital Re. Our voltage gain is V0 by Vi, that is equal to capital Re divided by small re plus capital Re. Remember this main equation. Then capital Re plus small re is capital Re only, because capital R is very much larger than small re. Therefore, here if we substitute small re plus capital R is capital Re, capital R and capital Re will cancel, and we get V0 is equal to Vi. That is, output voltage follows the input voltage. Similarly, we are finding the equation for the current gain. The equation for the current gain. First, we are finding the equation for I0 output current. V0 is equal to I into Re, that is minus I0 Re. We know that they are opposite in direction, IE and I0. Therefore, it is IE is minus I0. I0 it will be equal to minus V0 by Re, and we are writing equation for IA, that is Vi by Zi. Further, AI is equal to output current by input current. Substitute these equations, we get on simplification current gain is equal to minus AV into Zi divided by capital R. Remember this main equation for the current gain. Then we have discussed one example. We have solved an example on emitter follower circuit. This was the example that we solved in the previous class. Next is emitter follower circuit using voltage divider bias. Emitter follower using voltage divider bias. Here in this circuit, it is similar to voltage divider bias, but it is not exactly the voltage divider bias. Why? Because there is no collector resistance here. That is one reason. Another reason is we are tapping the output voltage from the emitter terminal here. But in voltage divider circuit, we are tapping the output voltage from the collector terminal. Right? That is the difference between emitter follower with the voltage divider bias and the main voltage divider bias circuit. We should be able to identify the difference between the two. Difference between main voltage divider bias circuit and the emitter follower with voltage divider bias circuit. Input current is II, input voltage Vi. There is a voltage divider here in between R1 and R2, and this circuit is called as emitter follower with voltage divider bias, or emitter follower using voltage divider bias. Then emitter resistance Re is there, collector resistance Rc is not there. Then the output is tapped from the emitter terminal. Input impedance Zi and output impedance is Z0. Output current is flowing into the transistor as per our convention, and hence it is I0. I naught is the output current. This is the AC equivalent circuit that we had drawn in our previous class for the emitter follower circuit. Emitter follower with voltage divider bias has the same AC equivalent circuit as that of the emitter follower circuit. The reason is, instead of RB, if we just look into the circuit here we had RB for the emitter follower circuit and there was a resistance RE. This R2 was not present. RB and then RE. But emitter follower with voltage divider bias has R1 and R2. What is this R1 and R2? It is nothing but parallel combination of R1 and R2. How do we get this? Parallel combination of R1 and R2. Now, if I make this VCC as 0, because it is AC equivalent circuit, we have to make the DC voltages off, or we have to make the DC voltages 0. If we make this VCC 0, then R1 will be connected between base terminal to ground. R1 will be connected between base terminal to ground, and R2 is also connected between base terminal to ground. R2 is also connected between base terminal to ground. That means R1 comes in between base terminal to ground in this circuit, between base terminal to ground, and R2 is also between base to ground. That means RB can be replaced by parallel combination of R1 and R2. RB can be replaced by parallel combination of R1 and R2, right? Therefore, here if we replace RB by R1 parallel R2, then that will give us the circuit, AC equivalent circuit for the emitter follower with voltage divider bias. Then emitter resistance is same between emitter terminal to ground, and collector terminal is also same between collector terminal to ground. Because we are making VCC 0, therefore the collector terminal will be connected to ground directly. That is, there is a collector to ground connection and emitter is connected to ground through the resistance RE. As we can see here, emitter resistance is connected from emitter terminal to ground, whereas collector terminal is directly connected to ground without any resistance. Input voltage is VI, input current II, input impedance ZI, then output current is I0, output voltage V0, and output impedance Z0. AC analysis for emitter follower configuration. Whatever was the analysis for emitter follower configuration, AC analysis of the emitter follower configuration, the same analysis can be used for the emitter follower with voltage divider bias circuit also. The reason I told, instead of just RB here, we are replacing RB by R1 parallel R2. This RB is replaced by R1 parallel R2. That is the only change, and other equations, everything analysis, everything remains the same for the emitter follower with voltage divider bias as that for the emitter follower circuit. Input impedance ZI. Here we are having input impedance ZI. It is RB parallel ZB. Just I repeated the equations for the emitter follower, right? What we discussed in our previous class. That is, ZI is given by RB parallel ZB. ZI is RB parallel ZB. Okay, RB parallel ZB, and hence RB is replaced by R1 parallel R2. RB is replaced by R1 parallel R2. This parallel ZB. Now ZB is given by beta into small re plus capital RE. Yes, just now I highlighted that equation. ZB is given by beta multiplied by RE, small re plus capital RE. Now small re plus capital RE is approximately equal to capital RE only, because capital RE is larger than small re. Therefore, I can write the equation for ZB as approximately equal to beta into capital RE. Okay. Now find the equation for output impedance Z0. Output impedance Z0, it is approximately equal to RE. What was the equation there we wrote for emitter follower? It was a parallel combination of small re and capital RE. Parallel combination of small re and capital RE. If we take the parallel combination, then we get small r into capital RE divided by small r plus capital RE. Correct? Now, small r plus capital RE is capital RE in the denominator. Therefore, we get the output impedance as small re into capital RE. In the denominator, we get it as only capital RE, because small r plus capital R is capital RE only. Capital RE in the numerator, capital R in the denominator cancels, and we get Z0 is approximately equal to R. This we have discussed in the previous class, how we are getting the output impedance as only the emitter resistance, that is small Re. Next is voltage gain equation, AV. This is also same as that for the emitter follower circuit, that is AV is given by capital Re divided by small re plus capital Re. AV is equal to capital R divided by small r plus capital R. Again, this can be simplified further. We know how to reduce it. Capital R plus small r is equal to capital R. That is, AV is equal to capital R divided by capital RE. Capital R and capital R cancels. Therefore, AV is approximately equal to 1. We say that the output voltage follows the input voltage, or output voltage is equal to the input voltage. Both are having the same phase, right? Both are in phase with each other, because V0 is equal to plus Vi. We say that both V0 and Vi are in phase with each other. Then the current gain equation is also same as that of the basic emitter follower circuit. V0, we got the equation there as IE into capital RE, or that is equal to minus I0 into capital RE, minus I0 into capital RE, because IE is equal to minus I0. Both are opposite in direction. Therefore, on further simplification, writing the equation for I0 and II, just we discussed at the beginning of this class, I0 by I ratio, if we take, then we get AI is equal to minus AV into ZI divided by capital RE. This is the equation for the current gain. That is, current gain for the emitter follower with voltage divider bias is same as that of the emitter follower circuit current gain equation. AI is equal to minus AV into ZI divided by capital RE. Clear here, students? This emitter follower with voltage divider bias is clear. Emitter follower with voltage divider bias is understood here. First, we have to know the difference between voltage divider bias and emitter follower with voltage divider bias. In voltage divider bias, what we are doing? We are taking the output from the collector terminal. We are taking the output from the collector terminal, whereas here we are taking the output from the emitter terminal. That is the main difference between voltage divider bias and the emitter follower with voltage divider bias. Okay. Then further, we obtained the performance parameters, that is input impedance, output impedance, voltage gain, and the current gain equations for the emitter follower with voltage divider bias. All the equations are same as that of the basic emitter follower circuit, except instead of RB, we have to replace that by R1 parallel R2. Everybody understood here this emitter follower with voltage divider bias? Is it clear? Abhay? Is it understood here, Abhay?
Yes, sir. Understood, sir.
Okay. Right. Ankita, is it understood? Ankita?
Yes, sir.
Okay, right. We'll proceed further. Emitter follower using collector resistor. Till now, we have seen emitter follower with voltage divider bias, but in the previous circuit, just we'll see the previous circuit. There is no collector resistance here. If you are seeing here, there is no collector resistance present. But in the next circuit, it is emitter follower with voltage divider bias considering the collector resistor, considering the RC resistance, collector resistor. Let us go to that circuit. This is the circuit, emitter follower using collector resistor. In the examination, if they ask, explain the AC analysis or the RE model of the emitter follower using collector resistor and its performance parameters, then you have to draw this circuit. To draw this circuit and then explain. We have resistance R1 and R2, that is the voltage divider between R1 and R2. Then there is collector resistance. There is a collector resistance RC, emitter resistance RE, emitter resistance RE, and the input is applied to the base terminal. Output is taken from the emitter terminal. Same, but there is RC present here. Then we have the I0 moving into the emitter terminal or moving into the transistor as per the convention. Input impedance is Zi, output impedance is Z0. So these are nothing but they are the amplifier circuits only. Whatever this common emitter, common base, common collector circuits, amplifier circuits are there, or configurations are there, they are nothing but the all are amplifier circuits. They are meant for amplification of the applied input signal. The presence of a collector resistance, it affects only the DC analysis of the circuit. So this RC resistance which is present here, this affects only the DC analysis. It does not affect the AC analysis. I will tell the reason for that. This RC is affecting only the DC analysis. If we make the KVL equation at the output side, if you write the KVL equation at the output side, and what we get, VCC minus ICRC minus VCE minus IERE is equal to 0. Write the KVL equation for the output section. VCC minus ICRC minus VCE minus IERE is equal to 0. That means this collector to emitter voltage VCE, it depends on the collector resistance RC. The collector to emitter voltage depends on the resistance RC. So we say that this RC affects only the DC analysis. Let us see how it does not affect the AC analysis. RC is not reflected, that is, it is not available or it is not shown in any of the derivations of the performance parameters for the circuit, right? And hence we say that RC is not affecting the AC analysis, because whatever equations were there for the emitter follower circuit, basic emitter follower circuit, the same equations we obtain for the emitter follower using collector resistance also. The equations remain the same as that of the basic emitter follower circuit. Okay, just we have to replace RB by R1 parallel R2. RB by R1 parallel R2, that will give us all the equations for the equations for the performance parameters of the emitter follower using collector resistor. Just we'll just analyze as to how this is not affecting the AC analysis, RC resistance. Let us go back here. So this is our main circuit. This is our main circuit, right? For the basic emitter follower circuit, it is AC equivalent circuit. Here we have RB, correct? Here we have RB. Instead of RB, we are having R1 and R2. Both will come in parallel. R1 and R2 both will come in parallel instead of this RB resistance. Okay, that is one thing. Then another one is here emitter terminal is connected through RE to ground. That is same. Then collector, here the resistance RC comes between collector to ground, because if you see this circuit there is resistance RC present in between collector to ground. We are making this VCC 0 for the AC analysis. That means RC is connected between collector terminal to ground. Collector terminal to ground. Yes or no? RC comes in between collector terminal to ground. VCC is 0. It is as good as ground, right? Now, if RC comes between collector terminal to ground, that means there is a resistance RC present here between collector terminal to ground. Now, even though it is present, even though the resistance RC is present, if we see the performance parameters, now let us see the performance parameters. Zi is given by beta into small re plus capital Re, correct? So here there is no RC term. RC term will never be highlighted here in the equation for ZB. Okay, and even equation for the Zi, it is RB parallel ZB, that is R1 parallel R2 parallel ZB. Again, there is no RC term. There is no RC highlighted in the equation for input impedance also. Let us check the output impedance equation, Z0. Z0 is approximately equal to small re. Again, there is no RC term. Then if we look the AV equation, voltage gain equation of the basic emitter follower, it is Re divided by small re plus capital Re, right? Again, there is no RC term here also. Therefore, Re plus small re, it is approximately equal to capital Re. Then we have gain is approximately equal to 1. What about in the current gain? Let us see. Current gain is obtained from V0 is equal to IE Re, that is minus I0 Re. Then final equation will be minus AV into Zi divided by Re. Again, if we see into this current gain equation, there is no RC term. What does it indicate? Even though the RC resistance is present between collector to ground or at the collector terminal, it is not affecting the AC analysis. It is not affecting the AC analysis of the emitter follower circuit using the collector resistor circuit. Okay. This is how we say that even though RC is present in the circuit, it is not affecting the AC analysis, but it does affect. It affects the DC analysis of the circuit. That is, DC analysis is affected by RC, but AC analysis is not affected by the resistance RC. Let us solve one example here. Take down this example. For the circuit shown below, calculate small re, a small re, b zi, that is input impedance, and z naught, capital Z naught, that is output impedance. Then AV voltage gain and AI current gain. Consider beta equal to 100 and R naught equal to 50 kilo ohms. Note down this circuit. Note down the circuit and note down the problem statement. I'll repeat. For the circuit shown below, calculate small re, second Zi and Z naught, input impedance and output impedance, third voltage gain and current gain, AV and AI. Consider beta equal to 100 and R naught, output resistance as 50 kilo ohms. Note down the circuit. This is R1 resistance 100 kilo ohms, R2 is 15 kilo ohms, then RC collector resistance is 4 kilo ohm, RE emitter resistance is 1.2 K. Input current is II, output current is I naught, output voltage V naught, input impedance is Zi, and output impedance is Z naught. VCC is 18 volts. Note down the circuit. Note down the circuit here. Just a minute. Please note down this circuit. 1 minute. Noted on the circuit here. Noted on the circuit. Shall we proceed?
Yes, sir.
Okay, fine. Here, if we look into this portion, that is R1, R2, then this RC, RE, it is the same as that of the voltage divider bias. This middle portion, right? Now, what is the change? Only change is output we are taking from the emitter terminal. Output we are taking from the emitter terminal, but not from the collector terminal. Okay, that is the only difference between main voltage divider bias and this emitter follower with voltage divider bias. Right, therefore VCC is 18 volts. Then here we are applying the exact method as we have discussed for the voltage divider bias. Right, if we use the exact method, in the approximate method, what we are considering, beta RE should be greater than 10 times R2. If we make use of the approximate analysis, the condition is beta RE should be greater than 10 times R2. Now see, beta they have given as 100 into R2, that is R2 is 15K. It becomes 150, 100 into 15. 100 into R2, right? That is how much we are getting, beta RE. Beta RE is less than 10 times R2. Beta into RE. What is beta? 100 into RE. Sorry, RE is here, emitter resistance. So 100 into 1.2K, 120K. It is 120K, 120K. 120K is less than 10 times R2. Less than 10 times R2. 10 times R2. What is R2 resistance? R2 resistance is 15K. R2 resistance is 15K. So 10 into 15 is 150K. Okay. So the condition for, if we want to apply approximate analysis, beta RE should be greater than 10 times R2, but here it is less than 10 times R2. Therefore, we cannot apply approximate method for analyzing this, or for obtaining the values for the given circuit. You have to apply the exact method. Now, if you are using the exact method, how we are doing the exact method? First, we are finding the RTH, that is R1 parallel R2, Thevenin resistance. Thevenin resistance is R1 parallel R2, R1 parallel R2. This is the Thevenin resistance, correct? RTH is equal to R1 parallel R2. Then what is the Thevenin voltage? How we are finding that? Can you recollect that? ETH is given by what equation? Can anybody tell me? ETH equation, Thevenin voltage. ETH is equal to what? Here we are obtaining the R1 and R2, they come in parallel, right? R1 and R2, they come in parallel, right? There is a VCC, right? For obtaining RTH, we are shorting the VCC. RTH is R1 parallel R2. Okay. Now for obtaining the ETH or the VTH, Thevenin voltage, right? We are keeping the VCC as it is, right? VCC is there, R1 is there. Okay. And then we have R2 at the junction. Correct. Try to recollect that circuit. Therefore, ETH will be main voltage, that is VCC. ETH is taken across R2, across this resistance R2, right? Therefore, ETH is main voltage, that is VCC, into resistance of the same branch, it is R2, divided by sum of the resistances R1 plus R2. ETH is equal to VCC into R2 divided by R1 plus R2. That is what it is written here. First, we are finding RTH, that is R1 parallel R2. R1 is given 100K plus parallel 15K, sorry, parallel 15K, that is, check how much you get, 100K parallel 15K, parallel combination of these two. Find out what is the value. 100K parallel 15K. Find out the value. Parallel combination of 100K and 15K. Tell me what is the value. How much you are getting? 100 kilo ohms parallel with 15 kilo ohms. 100K into 15K divided by 100K plus 15K. Parallel combination. R1 parallel R2. What is the answer? How much you are getting? R1 parallel R2.
$13K.
Yes, 13.043 kilo ohms. 13.043 kilo ohms. Fine. Next, ETH is given by VR2, that is voltage across resistance R2, that is voltage divider rule, VCC into R2 divided by R1 plus R2. Okay, VCC into R2 divided by R1 plus R2. VCC is 18 volts. This into 15K divided by R1 is 100K plus 15K. Calculate this value. VCC is 18, R2 is 15K, R1 is 100K. 18 into 15K divided by 100K plus 15K. Formula is, yes?
So answer is 2.347.
2.347, fine. ETH is given by 2.3478 volts. Okay. Then try to recollect what is the IB equation that we derived there. Okay, if we apply the KVL to this input section, right? Here we have ETH. VCC is considered in the ETH only, right? Therefore, the KVL equation for the input portion, for the input path of this circuit, emitter follower circuit, is given by ETH minus IB into RTH. Okay, ETH minus IB, that is base current which is flowing into the base terminal, that multiplied by the Thevenin's resistance, right? ETH minus IB into RTH minus VBE minus this base to emitter voltage minus IERE is equal to 0. ETH minus IB into RTH minus VB minus IERE is equal to 0. Okay. So if we simplify that equation, then we get IB is equal to ETH minus VB divided by RTH plus 1 plus beta into RE. Right. Just look into that equation. So that is how we are getting that VTH minus IB RTH minus VB minus IR is equal to 0. Right? Then IE we have to express in terms of IB. IE is equal to beta plus 1 into IB. Okay. Now if we substitute that equation, then we get VTH minus IB RTH minus VBE minus beta plus 1 into IB RE is equal to 0. If we take IB common, IB if we are taking common, then we get VTH minus IB multiplied by RTH plus beta plus 1 into RE minus VBE is equal to 0. VBE is equal to 0. And further, if we simplify, it is nothing but IB is equal to VTH minus VBE or ETH minus VBE. Both are one and the same. ETH minus VBE minus RTH plus 1 plus beta into RE. That is, ETH is 2.3478 minus 0.7. This divided by 13.043 K plus 101. 1 plus beta, 1 plus 100, that is 101 into 1.2 K. Answer is 12.2747 microampere. Just check this answer. You are getting this 2.4378 minus 0.7. That divided by 13.043 K plus 101 into 1.2 K. Don't look into the answer, just verify this. ETH IB is equal to ETH minus VB divided by RTH plus 1 plus beta into RE. How much you are getting? IB value? Yes. IB, how much you are getting?
12.27.
Correct. 12.2747 microampere. Okay. 12.2747 microampere. Now IE is given by 1 plus beta into IB. Agree with me? IE is given by 1 plus beta into IB. It is 1 plus 100 into IB. That is 101 into IB is 12.2747. Just now we obtained the value into 10 raised to minus 6. If we simplify this, just multiply whatever answer you have got now that by 101. Tell me how much you are getting. Just now you got the answer as 12.2747 microampere. Multiply that by 101 and tell me the answer. All of you should do this. Do the calculation. I may ask randomly anyone. Do the calculation. Rutvik Gune, have you done that? Rutvik Gune?
Sir, doing so.
Okay, do it. Just multiply that answer by 100. Previous answer we have got 12.2747 microampere. Multiply it by 100. 101, sorry, 101. Tell me in terms of, keep it in engineering mode. Keep your calc in engineering mode and tell me in terms of milliampere. Sanket, how much you are getting?
1.23 milliamps.
Very good. 1.23 milliampere. Correct. It is 1.23 milliampere. Now RE emitter resistance is given by 26 millivolt by I. What they have asked? They have asked to find the value of small RE. Okay, small R is given by 26 millivolt by IE. So we found out IE from 1 plus beta into IB. IB we got from this equation. Okay. Whereas we first found out RTH and ETH, substitute in this IB equation, we found out IB. Then in the IE equation, we substituted IB, we got IE in small R is equal to 26 millivolt by IE. That is 26 millivolt by 1.23 milliampere. Check out how much you're getting. 26 millivolt divided by 1.23 milliampere. Milli and milli will get cancelled. Just you have to divide 26 by 1.23. Tell me the answer. 26.26 divided by 1.23. How much is the answer? Yes, please. Divide 26 by 1.23. How much you are getting? Shiraj? Shiraj? Sai Prakash?
Sir,
Sai Prakash?
21.13. 21.13, sir.
21.13. Exactly. 21.13 ohms. Okay. Next, let us find ZB. ZB is given by the formula beta into small re plus capital R. The same formula as that for the basic emitter follower. Beta into Re plus capital Re, main formula, that is 100 multiplied by 21.13 ohms plus 1.2 K. Re is given in the circuit. Emitter resistance is 1.2 K. Substitute that. Tell me how much you get. 100 multiplied by 21.13 plus 1.2 K. Beta into small re plus capital R. Tell me the answer quickly. So we get 122.11 K. Just verify your answers. 122.11 kilo ohms. Next, we can find out Zi from this ZB, whatever we have obtained. Zi is equal to RB parallel ZB. So if we want to find out Zi, we need ZB. That's why we calculate ZB first. Then Zi is equal to RB parallel ZB. That is, RB is 100 kilo ohm parallel 15 kilo ohm. Okay. You have to replace RB by R1 parallel R2. R1 is 100 kilo ohm, R2 is 15 kilo ohm. Parallel combination just now we have calculated in part A of the problem. It is 13.04 kilo ohms. Therefore, Zi is 13.04 kilo ohm parallel with 122.11 K. Find out the parallel combination of these two. 13.04 kilo ohm parallel with 122.11 kilo ohms. Find out how much we get. One 3.0, that is 13.04 kilo ohm parallel with 122.11 kilo ohms. How much you are getting? Samir Ahmed, how much you are getting?
Calculating, sir.
Okay. Sania, have you done that? Sania? Shubham? Shubham? Found out the value? Suraya Banu? Tejas? Tejas. Who calculated that? Anybody calculated? Pratmesh? Pratmesh?
Sir, 11.78.
11.78, exactly. 11.78 kilometers. Fine. Similarly, calculate Z0. Z0 is given by capital RE parallel small re. Capital RE is 1.2K. It is given in the circuit. Okay. Parallel with small re. Small re we have calculated in party 21.13 ohms. Find out the answer. 1.2K parallel with 21.13 ohms. This is in kilo ohm. This is in ohms. 1.2K parallel with 21.13 ohms. Find out and tell me the answer quickly. How much you are getting?
Sir, 20.76.
Correct. 20.76 ohms. Fine. 20.76 ohms. So in part C, they have asked voltage gain and current gain. Directly apply the formulas. Main formula that we have already discussed in the basic emitter follower circuit, main emitter follower circuit. That is, AV is given by, the main equation is capital RE divided by small re plus capital RE. Just substitute the values. Capital R is 1.2K. This divided by small r is 21.13 plus 1.2K. The answer comes out to 0.983. Just verify your answers. 1.2K divided by 21.13 plus 1.2K. Are you getting this? 0.983? Are you getting the answer? 0.983? Getting that?
Yes, sir.
Fine. Good. Next, current gain. Apply the direct formula minus AV into ZI divided by capital RE. Current gain formula is AI is equal to minus AV into ZI divided by capital RE. AV just now we have calculated voltage gain, that is minus minus into 0.983. This into ZI we have calculated here 11.78 kilo ohms. This divided by capital RE. It is the circuit value, emitter resistance value 1.2K. Substitute, the answer will be minus 9.65. Just verify this. Minus 0.983 into 11.78K divided by 1.2K. K will cancel here. Just you have to find out minus 0.983 into 11.78. This divided by 1.2. Is it correct? Answer is correct here.
Yes, sir.
Minus 9.65 you are getting? Fine.
Yes, sir.
Very good. So that is today's topic, students. We have discussed in today's class emitter follower using voltage divider bias, emitter follower using voltage divider bias, right? How is it different from, how it is different from the voltage divider bias circuit? Okay, the main difference between the two. Then we have derived the performance parameters of the emitter follower using voltage divider bias by replacing RB by R1 parallel R2 in the equations of the emitter follower circuit. Various performance parameters: input impedance, output impedance, current gain, and voltage gain. Then emitter follower using collector resistor, RC, and we have again discussed here that RC does not affect AC analysis, but it affects the DC analysis. Again, we can obtain the equations just by replacing RB by R1 parallel R2 in this circuit also. Okay, and we have solved one example on the emitter follower using collector resistor. Right? Any difficulty here, students? In today's topics, any difficulty? Abhay?
No, sir. Understood, sir.
Understood?
Yes, sir.
Okay. Ratan? Birje? Janvi?
Understood, sir.
Understood? Fine. Ankita?
Yes, sir.
Okay. Sanket?
Yes, sir. Understood, sir.
Okay. Shubham? Understood? Tejas? Suraya Banu?
Understood, sir.
Understood. Any difficulty, Suraya Banu?
No, sir.
Any problem in understanding?
No, sir.
Okay, fine. Then we will continue in the next class. In the next class, we will start with the common base configuration. Okay. So we have start with the common base configuration, and then we'll derive the various performance parameters of the common base configuration, and then we'll discuss one example on that. Okay, that we'll take up in the next class. Thank you.